Hi everybody. So today I want to talk to you about heat, work, and the first law of thermodynamics. So in order to do that, I really have to talk about this guy right here, James Prescott Joule. Now, until the mid-1800s, the connection between thermodynamics and mechanics hadn't really been established. Now, James Joule, his family business was brewing beer, so an interest in chemistry and science came naturally to him. And science was kind of an interesting hobby. He was wealthy, so he had some money to spare to do these studies. So what he did was he performed experiments demonstrating the link between the mechanical motion of objects and the heat. He attached weights to ropes and pulleys, and then he let the weights fall. And the falling weights then pulled on the ropes, which turned the paddle wheel, which was inside a big container of water, and a schematic of the apparatus is shown here. Because the container was insulated, what happened was that as the paddles turned in the water, there was friction there which heated up the water, and the temperature of the water rose. And he was able to relate in equations the temperature of the water to what was going on with the heat. Now, when he did this, he established the link between the mechanical energy of the falling weights and the internal energy change of the water. Now, we've already discussed in a previous lecture state variables. State variables describe the state of a system. These are variables such as the pressure, volume, temperature, number of particles, things like that. There's also so-called transfer variables. Now, transfer variables are zero unless some kind of process occurs that transfers energy across the boundary of a system. Transfer variables aren't associated with any given state of the system, only with changes in that state. And we're going to define two of those transfer variables: heat, which we'll symbolize with Q, and work, which are W. Now, the significance of Joule's work was that these experiments led scientists to understand that conservation of energy was a universal law of nature, that you could have a change in the mechanical energy of the system, and that energy could then be transferred to the internal energy of the system. This caused a rejection of the so-called caloric theory in thermodynamics. And this now obsolete theory hypothesized that there was a fluid called a caloric, and then that fluid flowed from hotter to colder bodies, which caused a change in temperature. And this is where we get the name calorie, which is a unit of energy. We now know that energy is transferred via heat or work and not the caloric. We define heat as the transfer of energy across the boundary of a system due to a temperature difference between the system and its surroundings. There's generally three mechanisms for heat transfer: convection, conduction, or radiation. We'll talk about those later. Work in thermodynamics is defined as any other transfer of energy into or out of a system. This work can be electrical, like for example running a current through a wire which causes a medium to heat up, or it could be a push or a pull, like Joule's paddle wheel, and there's a lot of other forms of work too. Now, the first law of thermodynamics is a special case of the law of conservation of energy. It takes into account changes in internal energy and energy transfers via heat and work. The first law of thermodynamics states that the change in the internal energy of the system, which I'll call delta U, is equal to the sum of the heat and the work. So all quantities in this equation must have the same units of measure of energy. The joule is the SI unit of energy, named in honor of James Prescott Joule, who we just talked about. There's also the calorie, which is a non-SI unit of energy. To convert between calories and joules, 1 calorie is 4.186 joules. You might be most familiar, with the unit of energy called the food calorie. This is what appears on packages to tell you how fat you're going to get from eating that bar of chocolate. 1 food calorie is actually 4,186 joules. So the calorie that we discuss in thermodynamics, that's actually a kilocalorie if you're talking about food calories. Okay, let's talk about a special case for work. Oftentimes we talk about compressing or expanding gases. This is useful in heat engines, for example, where you have pistons. So we're going to call this compressive work. We're going to go through a whole different kind of processes and talk about those for work in thermodynamics. So compressive work can be done on a deformable system like a gas. And like I said, cylinders and pistons are really common examples that we use in thermodynamics for obvious reasons, that we have a whole bunch of cars out there that are running on pistons. So in this little example here to the right, a force is applied slowly to compress the gas. Okay? So you have a piston attached to a rod, you push on the rod, and that pushes the faceplate down of the piston, compressing the gas. Now, let's assume for a second that this compression is slow enough for all the system to remain essentially in thermal equilibrium. That's a quasi-static change. So what we can do is we can solve for the equation for compressive work. If you push the piston downward by a force through a displacement, remember that the formula for work is the dot product of the force with the displacement. So if we assume that equation is F dot dr, then for this case we can say that it's minus F. If we take the up and down version as the j hat direction, then the displacement is in the negative y direction. So that would be the force, which is in the j hat, it's a downward push, dotted with delta y in the j hat. And this is minus F dy, okay? Minus F dy. Now, the force is also a product of the pressure with the area. So that's minus PA dy, okay? So A dy is the change in the volume of the gas. So if you look at A as the area of that faceplate, then A times dy would give you a volume. And we'll call that volume change dV. Therefore, the work done on the gas is minus P dV. Now, if we want to interpret this, dW is minus P dV, so for a little differential change in the volume, you get a differential change in work, okay? Now, if the gas is compressed, dV is negative, and the work done on the gas is positive. If the gas expands, dV is positive, and the work done on the gas is negative. And if the volume remains constant, of course, the total work done is zero. There's been no change. We can write the equation for the total work via integrating both sides, and then we would get the work is equal to minus the integral of P dV. Now, just to emphasize, because sometimes students get confused about the signs, the work done on the gas is work is equal to minus the integral of P dV. The work done by the gas is the positive integral of P dV. So that's the signs. Now, lots of times we like to have a visual representation of a process in thermodynamics, and we oftentimes use what's called a PV diagram to do this. So in a PV diagram, you plot the pressure and the volume for each step of a process, okay? That's done here. So the process is along this orange line, and you can see that the arrow indicates which way it goes. So you start off here at a smaller initial volume and pressure. We label that initial point I, and then it continues along the path up to the final point, okay? Now you can see here that on a PV diagram, the work, the way that we've written it, is, or drawn it, is the area under that curve. So what that means is that the work is path dependent. There's several examples of that here. All three of these processes have the same initial and the final state, but you can see that the work underneath the curve changes dramatically depending on how you get to the initial and the final state. So for example, here in case A, you have the least amount of work under that, the least amount of area under that curve, so that kind of process is the least amount of work. If you go along a different path here in point B, then you go up and then across, that's going to be the largest area under the curve, so that's the most work. And then here's the one that we did initially, which is sort of a medium amount of work, okay? So the work differs in each process. The work done depends upon the path. Let's talk about a couple of specific examples and how they might apply to the first law of thermodynamics. Remember that the first law of thermodynamics is the law of conservation of energy. So any change in the internal energy of the system, delta U, is going to equal to the sum of the heat plus the work, okay? Now, the energy transfer via heat, Q, into or out of a system also depends on the process or the path. And that's because what happens is delta U, the change in the internal energy of the system, is directly related to the temperature of the system in its initial and final state, right? Delta U is going to equal to NR F over 2 delta T, okay? So, where F is the number of degrees of freedom. Now, because the work depends upon the path, and the internal energy is the sum of the heat plus the work, right? The internal energy is only dependent upon the temperature of the system, but the work is dependent upon the path, and the heat therefore must also be dependent upon the path. All right? Now, how could that happen? The energy reservoir, we're going to define that term. An energy reservoir is a source of energy that's considered to be so great that a finite transfer of heat energy into or out of it doesn't really change its temperature. Okay? Now, we often assume that being allowed to exchange heat with the outside world means that the system is in contact with an energy reservoir. You can think of it as if you have an engine sitting there running inside of a room, the engine can dump heat into the room, so it's dumping heat into that energy reservoir. Okay? Now, usually you have to insulate a system if you want to prevent energy from being transferred into or out of a system. So it's actually kind of difficult to not have your system in contact with some kind of energy reservoir. So here you can see that you've got a piston and it's got insulating walls everywhere except there at the bottom where it's in contact with that energy reservoir. And then if you pull up on that piston slowly enough, and your gas is at initial temperature, which is the same as your reservoir, and you pull up slowly enough, then heat energy can be transferred to and from through that contact with the energy reservoir, and that'll maintain a constant temperature. The thing to remember about that, though, is that if you do it fast, there's not going to be enough time for heat to be transferred through that reservoir. If you think about it, all the three processes, conduction, convection, and radiation, which control heat transfer, all of these are rate-dependent processes. So if you do something really fast, take it through a fast process, you're not going to have time, okay, for that energy transfer to take place. So it's kind of tough sometimes. Okay, so here we have situations A and B. We're going to assume for the moment that these two containers are basically the same size. Now the container on the left has contact with an energy reservoir at a temperature Ti. So here heat energy is allowed to be transferred to and from this system, from the reservoir. Now on the other hand, on the situation on the right, situation B, this is entirely contained within insulating walls. So in this case, you're not allowing the system to exchange energy with the reservoir, so it's an isolated system. Okay, now if you look at the situation on the left and the situation on the right, and assume that those containers are the same size, okay, then you've got kind of an interesting conundrum. If you're in situation A, the gas expands as you pull up on that piston, okay? Normally, this would lower the temperature. The expansion of the gas would lower the temperature. But the temperature remains the same in this case because heat is being transferred from that bottom reservoir. We're doing it slowly enough that the transfer of heat can take place. All right, now let's look at situation B on the right. For B, no energy is transferred via heat through that insulating wall. However, there's no work done here. The reason is that there's no piston to push on in this case, and the gas that's initially contained by that little membrane there, it just expands into a vacuum. So there's no gas to push out of the way either, okay? The membrane just pops, and then it expands that gas into a vacuum. So there was nothing there, and there's nothing to push out of the way. So what that means is if you contrast those two cases, the temperature isn't going to change in either case, right? It doesn't change in case A because it's in contact with that reservoir and the temperature remains the same. It doesn't change in case B because there's no heat change, no heat exchanged, and no work done. And if there's no heat and there's no work, then there's no change in the internal energy, right? So that means that the temperature doesn't change, okay? Case B from the previous slide is actually really unusual because it's an isolated system, and true isolated systems are rare. You don't often have gases expanding into vacuums. It doesn't happen a lot. An isolated system is one that doesn't interact with its surroundings. No energy transfer via heat takes place, and the work done on the system is zero. So, since the heat and the work are both zero, the change in the internal energy of the system is zero, and the temperature remains constant. This would be tough to do, like I said. You'd have to do it in a lab, and you'd need perfect insulation and something like a membrane that could be popped without any work being done. So it's tough. You can simulate it, maybe you can come close. All right, let's talk about another kind of process. So we talked about isolated systems. Now let's talk about cyclic processes. These occur a lot in engines. A cyclic process is one that starts and ends in the same state. Okay? This would not be an isolated process. On a PV diagram, since it starts and ends in the same place, you're going to have closed curves. So here you can see it starts off in the lower left corner of this little rectangle, and then the pressure increases to 3P while the volume stays constant, and then the pressure increases while the volume stays then the volume increases while the pressure stays constant, and then the pressure drops while the volume stays constant, and then the volume reduces while the pressure stays constant, and then you're back at point A. Okay? So that's the situation. Now, if you look at the entire cycle, right, and what happens when you start at the initial point and then come back to the initial point, the internal energy change for the cycle must be 0, right? The internal energy must be 0. Change in the internal energy must be 0. And that's because you're comparing what's happening at PI and VI, and then you go all the way around and you come back to PI and VI. So you're at the same point, the same state as you were when you first started. If it's in the same state, there's no change in internal energy. All right, since the change in the internal energy is 0, delta U is equal to 0, then over the course of the whole cycle, the heat has to equal to negative of the work, right? 0 is equal to Q plus W, so Q has to equal minus W. Now this isn't to say that for any particular step in the process, for example going to A and B, that this will be the case, all right? It's not the case for any step. What we're talking about is what happens over the course of the entire cycle. Okay, now in a cyclic process, the net work done on the system per cycle is going to equal the area enclosed by that curve, right? So you just have to figure out the shaded area here, and then that'll give you the work. Let me do an example problem so that it's cemented in your head. The gas at the right is taken through the cycle. So find the net work done on the gas in the cycle, and what's the net energy added by heat in the cycle. Obtain a numerical value for the work for 1 mole of an ideal gas at an initial temperature, which is at point A here, of 273 Kelvin. Okay, so the work is the area enclosed by the curve. This is a rectangle, right? Now, is that work negative or positive? Well, if we look back, you can see that along the top of the rectangle, the volume is expanding as it goes from B to C. Now, it's the work is the area enclosed by the curve because if you look here, the area underneath B to C minus the area underneath A to D would give you that area of that rectangle. So we say that it's the area enclosed by that curve for the work for the whole cycle. All right? Okay. Now, since B to C is an expansion, then that means that delta V is positive, and that means that the work done on the gas is negative. Okay, here we go. Since there's no net change in the internal energy, the heat added will then be positive over the entire cycle because minus the work equals the heat. Now the area of that rectangle would be 3pi minus pi, which is 2pi, times 3vi minus vi, which is 2vi. So that's 2pi times 2vi, and that's minus w, which is equal to q, which is equal to 4pi vi. Now, we don't know what pi and vi are, but we do know that we can use the ideal gas law to solve for the product of P and V, because PV is equal to nRT. So PI/VI is equal to nRTI. We have 1 mole of gas, so that's N. R is 8.314 joules per mole Kelvin, and the temperature is 273 degrees Kelvin initially. If we multiply those numbers, we get 2,270 joules. Now, the work minus the work is equal to 4 times PI/VI. So if we multiply 4 times 2270, then we get 9080 joules. So negative the work is equal to the heat, which is equal to 9,080 joules. Moving on to a different kind of process, an isobaric process is defined as one that occurs at a constant pressure. These are horizontal lines on PV diagrams. So in examples A and B here, along the bottom portion of this horizontal line, that's a constant pressure process, and so is the top here in example B. Now, for these cases, the values of the heat and the work are generally both non-zero. So being isobaric doesn't tell you anything straight off about what the heat or the work is. It's not like a cyclic process where we know that the change in the internal energy is zero, so minus the work has to equal the heat. We don't know anything like that about isobaric processes. If you solve using the equation, the work is equal to the negative integral of P dV. If P is a constant, then you're just integrating dV, and when you do that, you get delta V. So the work done is minus P times V final minus V initial, where P is that constant pressure. Now remember, pressure units can get a little strange, so if you want your final answer for the work to be in joules, which you usually do, then you're going to need to convert your pressure units over to pascals, which is the SI unit, and you're going to need to convert your volume to meters cubed. Alright, let's do an example problem. Suppose you have 4 moles of a monatomic gas at a temperature of 293 Kelvin, and it undergoes a constant pressure expansion from an initial volume of 30 liters to a final volume of 60 liters. What's the final temperature of the gas? What's the change in the thermal energy of the gas as it undergoes this process? And what's the work done on the gas? Alright, so first, we have to use the ideal gas law, which is of course PV is equal to nRT, to solve for the unknown pressure, because we weren't given the pressure in this question. Since we do know the initial temperature, we can use the initial conditions to solve for the pressure, which will remain constant. So plugging into PV is equal to nRT, I have P times 30 liters, which is equal to, I'm going to use the gas constant 0.08214 liters atmospheres per mole Kelvin. And then I'm going to multiply the gas constant, R, times N, which is 4 moles, times the temperature, which is 293 Kelvin. Solving, I can then get pressure in atmospheres, and the pressure is 3.21 atmospheres. Now, since I know that this is pressure that's going to remain constant throughout the process, we can use the final conditions to solve for the final temperature, which was asked for. And we're going to use the ideal gas law again to do that. If you rearrange the ideal gas law, you get that T final is equal to PV final divided by NR. Plugging into that, I get 3.21 atmospheres times 60 liters divided by 4 moles divided by 0.08214 liters atmospheres per mole Kelvin. Solving then for the temperature, I get 586 Kelvin. Now, since we have the temperatures, we can now solve for the change in the internal energy. Our expression for that is delta U is equal to NR delta T. Delta U is the change in the internal energy, delta T is the change in temperature. So we can solve for delta U. N is 4 moles, R is 8.314. That's a typo. Okay, now it's fixed. It was right in my notes and not when I typed it onto the slide. Delta U is NR delta T, where N is 4 moles, R is 8.314 joules per mole Kelvin, and delta T is 586 minus 293 Kelvin. So that gives me, when I multiply all those things out, 14,620 joules. Okay, we can now solve for the work done on the gas. Note that 1 liter here is 0.001 cubic meters, that's the conversion from liters to cubic meters, and also that there's 1.013 times 10 to the 5th pascals per atmosphere. I'm going to use both of those conversions here. The work for an isobaric process is work is equal to minus P delta V. So I'm going to change over 3.21 atmospheres by multiplying by the conversion constant 1.013 times 10 to the 5th pascals, and then I just went ahead and straight up converted the liters. 60 liters is 0.06 cubic meters and 30 liters is 0.03 cubic meters, and I subtracted those two numbers. Then when I solve this equation, I get minus 9,755 joules for the work done on the gas. Okay? So what that means is that if you wanted to solve for the heat, you would do delta U is equal to Q plus W, and then you would see that there had to be heat transferred to the gas in order for this process to take place. Next type of process I would like to talk about is isovolumetric processes. An isovolumetric process is one in which there is no change in volume. Since the volume doesn't change, that means that the work done on or by the gas is zero. And then from the first law, any change in internal energy has to come from the heat. So if energy is added by heat to a system kept at a constant volume, all of the transferred energy remains in the system as an increase in its internal energy. It heats up. The next kind of process that I'd like to talk about is an isothermal process. An isothermal process is one that occurs at a constant temperature. On a PV diagram, what happens is they are hyperbolas, okay? And we call these hyperbolas isotherms. Now, since there's no change in temperature, delta U is equal to NR delta T, that means that the delta U is equal to 0 for isothermal processes. There's no change in the internal energy. Therefore, the heat equals the negative of the work. So any energy that enters the system by heat must leave the system by work, or vice versa. In reality, isothermal processes are usually slow because heat transfer takes time. And it takes time to keep a system at a constant temperature. You have to go through the process slowly in order for that to happen because heat transfer is a rate-limiting process. If you want to solve for the equation for a work in an isothermal process, you can do that for an ideal gas. If you use the ideal gas law, PV is equal to nRT, and plug in for the pressure, then you get the pressure is equal to nRT over V. Now, since in an isothermal process we're assuming that the number of moles don't change and that the temperature is the same, you can pull those constants nRT outside of the integral. So then the equation for the work, which is originally the negative integral of PdV, becomes the negative integral of nRT times the integral of dV over V. Okay, so work is equal to minus nRT times the integral of dV over V. When you integrate 1 over V, you're going to get a natural log. Evaluating from the endpoints, you're integrating from V initial to V final, then what you end up with is nRT times the natural log of V initial over V final. Let's do an example problem with this. During an isothermal process, 0.6 moles of an ideal gas expands to a final volume of 9 liters in 2 atmospheres of pressure while doing 3 kilojoules of work on its surroundings. What's the initial volume of the gas, and what's the temperature of the gas? Okay, so there's two unknowns here, the temperature and the initial volume. The temperature remains constant throughout the process, so we don't have to worry about initial and final temperatures. We're going to first use the ideal gas law, PV is equal to nRT, to solve for the unknown temperature using the final values of temperature and pressure. Okay, so here we have PV is equal to nRT. If I plug that in, then I have a pressure of 2 atmospheres, which usually in the conversion is 2.026 times 10 to the 5th pascals, and we have a volume of 9 liters, which is 0.009 cubic meters, and then that's equal to 0.6 moles times 8.314 joules per mole Kelvin times the temperature. Solving for that, we get a temperature of 365.5 Kelvin. Now we can use the equation for work to solve for the initial volume. The work is equal to nRT times the natural log of V initial over V final. The work is going to be minus 3,000 joules. If you set that equal then, that minus 3,000 joules, to nRT times the natural log, so you get 0.6 moles times 8.314 joules per mole Kelvin times the temperature, 365.5 Kelvin, times the natural log of V initial over V final. Dividing out by those constants, you get that the natural log of V initial over V final is minus 1.645. Now, if you raise both sides, e to the power there, then on the left-hand side you'll have V initial over 9 liters is equal to e to the minus 1.645, and then that gives you 0.193. You can then multiply both sides by 9 liters to solve for V initial, 1.74 liters. Moving on, let's talk about adiabatic processes. Adiabatic processes mean that no heat is transferred to or from the system, or Q is equal to 0. These processes could be carried out in an insulated container, but the most common explanation is that they just happen really fast. If they're rapid, then there's no time for heat to be transferred to or from the system. As we said, to maintain an isothermal process, that's going to be kind of slow. Adiabatic process, on the other hand, can be fast. Physical and chemical processes that are very rapid are often approximated as adiabatic for this reason. What we might need if they're approximately adiabatic is just that not much heat energy is transferred, so you can neglect it. Now on PV diagrams, an adiabat is actually steeper than an isotherm, so you can recognize them by how steep they are compared to the relative isotherm. Now, since Q is equal to 0, the change in the internal energy, which is usually equal to the heat plus the work, is only the work here. Now, we know from the equipartition theorem that U is equal to the number of degrees of freedom F divided by 2 times nkt. So any change in U, du, is F over 2 nk dt. Okay? Now, this is also, since there is no heat, equal to dW for the work, which is equal to minus PdV. Okay, so using the ideal gas law, PV is equal to nkt. Rearranging that, we can solve for the pressure, which is nkt over V. Plugging that into this expression that we just wrote, F over 2 nk dt is going to be equal to minus nkt over V times dV. Okay? Now, F over 2 nk dt over t is equal to minus nk dV over V. We can cancel out the nk from both sides and get F over 2 dt over t is equal to minus dV over V. Then we can integrate both sides of that equation, and since we've got a 1 over t on one side and a 1 over v on the other side, we're going to get two natural logs. So that leaves us with F over 2 times the natural log of t final over t initial is equal to the minus natural log of v final over v initial, or the natural log of v initial over v final. Now, using some more laws from logarithms, if you've forgotten them, they're on the slide there at the top. That gives us F over 2 times the ln of t final over t initial, which is equal to ln t final over t initial raised to the F over 2 power. And then this is equal to the natural log of v initial over v final. If you then raise both sides to the power e, then you have t final over t initial is equal to F over 2 is equal to v initial over v final. Raising that e cancels out the natural log. And then you can rearrange that equation just by cross multiplying and get v final, t final to the F over 2 power is equal to v initial, t initial to the F over 2 power, which means that this product is a constant throughout the process. So, Vt to the F over 2 is a constant. If you use the ideal gas law and solve for T and then plug in for that, you get V times PV over NR to the F over 2 power. Now let's assume that N and R are constant, so they can be multiplied to both sides there and get sucked into that same constant, so that we then have V times PV to the F over 2 equals to a different constant. Okay? Now, I've got two V expressions there raised to different powers. One is V to the 1 and the other is V to the F over 2. What that gives me then is V to the 1 plus F over 2 power times P to the F over 2, and that's a constant. Okay? Now, I'd like to cancel out that F over 2, so I raise that left-hand side to the 2 over F power. Remember, when I do this, I'm still not changing anything. It's still going to be a constant. It's just a different constant. For our purposes, though, that doesn't matter. Okay? So if I raise that to the 2 over F power, then I get PV to the 2 over F plus 1 power. Rearranging that power using a little bit of algebra, I get PV to the F plus 2 over F, and that's still a constant. We often call this value, F plus 2 over F, gamma, and we say that gamma is equal to F plus 2 over F. Remember that F is the number of degrees of freedom that you have. For a monatomic gas, then F is going to be 3. For a diatomic gas at room temperature, F will be 5. And we'll talk more about that in a different lecture. Now at room temperature, diatomic gas here undergoes an adiabatic process such that its final pressure is 3 times its initial pressure. Did the gas expand or contract, and what's the ratio of its final to initial volume? Let's do this example together on adiabatic processes. So, PV to the gamma is a constant for adiabatic processes. This implies that if the pressure goes up, the volume has to go down in order to keep the process product the same. So that tells us what happens to the gas. Now, for a diatomic gas at room temperature, there's 5 degrees of freedom, like we talked about. This includes the 3 translational and 2 vibrational degrees of freedom. The rotational degrees of freedom are locked out at room temperature, so you don't need to consider those. So this means that gamma, which is F plus 2 over F, is 7/5. So we have P initial V initial to gamma equals P final V final to gamma for adiabatic processes. So P initial V initial to the 7/5 power is equal to 3 times P final V final to the 7/5 power. Here we're just plugging in that P final is 3 times P initial. Canceling out the P from both sides, we have V initial to the 7/5 is equal to 3 V final to the 7/5. Rearranging that, I get 1/3 is equal to VF to the 7/5 over VI to the 7/5. Now if I raise both sides of that to the 5/7 power, I can cancel out my powers. And I get 1/3 to the 5/7 power is equal to V final over V initial. Solving for 1/3 of the 5/7 power, I get 0.456. So that's the compression or ratio that it was asking for in the previous question. Okay, I hope that was relatively followable. If you had a little trouble at any given point, don't forget you can always go back to that point in the video and watch it again. Always remember you can pause me at any time. I know that some of this stuff is starting to get confusing. Alright, I hope if you have any additional questions, I'll see you in class.